Okay. So we're leaving to the side for the moment all the multivariable calculus we were doing last term, and we're now going to start a completely different topic, which is called Laplace transforms. And what this is, it's a certain method. What this is going to mean for us is it's a certain method for solving certain types of differential equation. Okay? The kind of objects we're going to be solving are differential equations that look like this one here, in equation 2.1. And these are so-called so-called linear differential equations, constant coefficients. The ordinary differential equation part means that there's an unknown function here, and so here the unknown function is y of t, and it's a function of a single variable, t. That's the ordinary bit, ordinary as opposed to partial. Partial differential equations is where the unknown function is a function of a number of variables, and the equation features partial derivatives. These are ordinary differential equations, an unknown function y of one variable, and there's various derivatives of y there. The linear bit refers to the fact that in the structure of the equation, we never see different derivatives multiplied by each other, or any individual derivative raised to some power. Okay? The way derivatives occur in the equation is they just occur on their own, maybe multiplied by a coefficient, which does not depend on t. But you never see a derivative raised to a power or two different derivatives multiplied together. Okay? That would be nonlinear behavior. So the adjective linear refers to the fact that we don't see that go. There's coefficients here. Now, when we say constant coefficients, what we mean is these coefficients, a0 up to an on the left-hand side of the equation, that these are constants. They do not depend on the independent variable t. Okay, so they're just number quantities. With the exception of the constant coefficient to the equation. So the constant coefficient is the one that isn't multiplied by a y or a derivative of y. That's, if you like, the constant coefficient in the equation. In our setup, that is allowed to be certain types of function of t. So the constant coefficient can be a non-constant in the sense that it can have a dependence on the independent variable t. Okay? So objects like this are going to be the ones that we're going to be solving. And we're going to be solving them with this device or concept called the Laplace transform. Now, before we get into it, I just want to give you an analogy, an example of a completely different situation where we see a certain type of thing going on. It's something like a transform going on. And that's going to motivate or give you some kind of framework to attach and understand what's going on with the Laplace transforms. Because the way the Laplace transform solution method is going to work is we're going to transform the equation. We're going to take the equation that we're trying to solve, the differential equation, and transform it so that it looks a lot different. So it'll no longer feature derivatives. We'll transform it into a separate kind of equation, a more algebraic kind of an equation. The other equation will feature an unknown quantity, which is going to be the transform of y. So it'll be some object related to y. That'll be the transform of this unknown function y. But we're going to transform the equation first and solve the transform first, because that's easier to solve. We don't need any kind of particularly sophisticated techniques to solve it. It can just be solved by algebraic manipulation. But that solves the transfer problem, but what we're interested in is solutions to the original problem, the original differential equation. So the last step in the process is going to be applying the inverse transform. We apply the inverse transform, we come back into the context of the differential equation, and we get back a function of t, which is the solution of this original. So that's the kind of overall framework where we're going to have this initial problem, which is too hard to solve directly. We're going to transform it to a related problem in a different context, which we can solve using kind of just straightforward algebraic manipulation. And then we do the kind of inverse transform to bring the solution of the transform problem back into the context of functions of t and so on. But the related setup is to do with log tables. If you Google log tables, you get two kinds of things occurring. They were not interested in these ones so much. Still gets, I think I've done that joke 3 years in a row. It still works. This is the kind of thing we're interested in. Log tables. So these are not so much familiar to us now, okay, with the advent of calculators and computers. Okay. So what were these? So this is a table of values of the logarithm function to base 10. This is actually, it just so happens this is an Irish one, because the logarithm Gabun 10 is Irish on the left-hand side. This must be from the Irish Department of Education. Okay? So before calculators, people used these laboriously calculated. So people sat down and prepared these tables. So this shows, so for instance, the logarithm to the base 10 of 2.9 is 0.4624. And if it's 2.95, you come across here, it's whatever it is, 0.4698. So it tells you what values of the logarithm function are. And you can also use it in reverse as a table of values of the exponential function. So for instance, if you want to know what the exponential of 0, or not the exponential, the exponential with base 10. So if you want to know what 10 to the power of 0.85 is, 0.85 is over here. So 10 to the power of 10 to the power of 0.85 is 7.9. Okay. So this table of values allows you to apply the logarithm function and to apply the exponential function. Okay, why did people put so much effort into constructing these? So these would, pre-electronic calculators, these would have had to be calculated either using mechanical calculators or literally by hand using some kind of approximation methods like Taylor series or some other kind of series functions, polynomial functions approximating the logarithm that people could calculate out. So why were these kind of things constructed? I mean, you still use these tables in a sense. I mean, you've been using tables like that in statistics to read off values of the distributions, the various probability distributions. So we still use them in that context. We don't use them really so much for other functions like logarithm, exponential, and so on. So what use were logarithm tables? Well, one main use of logarithm tables were to help in certain types of hard problems. And the certain types of hard problems were if you wanted to evaluate, say, one number raised to the power of another one. Or maybe not so hard, but still maybe a little bit hard if you wanted to multiply two numbers. Okay. What's so hard about that? Well, okay. If A and B are not integers, if A and B are complicated numbers, if they're fractions with large denominators, or if they're decimal numbers with a few decimal places, then raising two of those numbers to a power of each other or multiplying them. Remember, if you don't have calculators or computers. Okay, multiplication isn't so hard. You can do long multiplication. To learn it in primary school, it's not that hard. But certainly raising A to the power B, when A and or B might be numbers with decimal places, it's not so straightforward to calculate. So this is where the log tables come in. Now it's not so important what the base of the logarithm is, whether it's base 10 or base e, the natural logarithm, or some other base. The important thing is what happens when you take the logarithm of a to the power b. Remember, we don't know what the value of this thing is because we're faced with this hard problem of evaluating this. But we do know something about the properties of the logarithm function. So that simplifies a bit, doesn't it? Into what? B times log a. So that exponent there magically pops out of the logarithm. And we got b times log a. And if we take the logarithm of a times b, that simplifies a little bit. Log a plus log b. Now what's happened here? What's happened here is, faced with this original problem of evaluating power like this, has kind of been replaced by evaluating a product, which looks easier. And the slightly easier problem, but still maybe hard, of multiplying together two arbitrary numbers has been replaced by the easier, quicker problem of just adding two numbers. Not the original numbers a and b, but adding their logarithms. I'm not multiplying the original numbers a and b, but, well, multiplying b by the logarithm of a. So these problems here on the right-hand side are easier to evaluate, provided we know what the logarithm of a is and the logarithm of b is. Okay? So that's taken care of in the table. Okay? People went to the trouble of constructing the table. You only have to do that once. When you had the table, you could use it again and again. So we can read off using the table in our pre-calculator days, pre-computer days. We can read off what the logarithm of a is, or what it approximately is. And similarly, logarithm of b. And we can evaluate these right-hand sides. So the right-hand side here of these equations is easier to evaluate. But we want these quantities over here. So how do we get these quantities now? Well, we have to reverse the transformation. And the reverse of the logarithm transformation is the exponential transformation. So if this was log to the base 10, we go back, we do the function 10 to the power of whatever the argument is. So these quantities here, when you work them out, when you evaluate them, you raise 10 to that power, and that brings you back here and gives you an approximation to these values over here. So the logarithm and exponential going the other direction. Remember, these values were tabulations. So to work out 10 to the power of something, you could make use of the table to do that. That wasn't a hand calculation you had to do necessarily. So the logarithm and exponential functions, or let's call them transforms, they're not transforms in the technical sense of what a transform is, but let's just speak of them like that for the moment. So the logarithm and exponential transforms make evaluation of powers and products easier. Okay, so that's why they were used. People doing computational mathematics before they had calculators and computers available would quite often make use of logarithm and exponential tables just as an everyday tool for carrying out calculations. You don't need it now because the computer takes care of it for you. Okay? But it's interesting to see. So what we want to take from that, I mean, why are we doing this? This gets across this idea, so something you're already familiar with, but it gets across the idea that you're faced with a certain kind of a hard problem here, evaluating these things. You translate it or transform it into a different context. Rather than the original values, you're now talking about the logarithms of it. You solve the problem over there. You solve the problem of evaluation over here. It's easier than the thing you were faced with originally. The answer that you get over here is not the answer to your original problem, but you need to transform it back using the exponential function. Transform it back, again, reading off values off the table. You get back the answers to your original problems. Okay? So hard problem, transform it, an easier problem, solve the easier problem, and then transform it back, we get the solution to the original problem. Okay. That's the framework of how Laplace transforms work for solving a differential equation. Okay. And the details are different. It's not the logarithm, it's not the exponential, it's different things. Okay. Any questions about just that example? Okay. Okay, then let's meet the transform. Say hello to it. Okay, here's the transform. Now, this is an object that's going to apply not to numbers, so the logarithm applies to numbers. But our transform, the Laplace transform, is something you do to a function. Okay, to a whole function. So what it does is it takes a function of t, say, so a function of a single variable, and the transform is a rule for associating a new function to the original function x. They're going to refer to the new function as capital X. It's a different function. And importantly, it's a function of a new and different variable, s. Okay, so it's not a new function of t, where t was the original argument of x. It's a new function, and there's a new variable introduced, new variable s. Now this new function, of course, depends on the original function x. So the values of the original function x are somehow used to define this new function in capital X. And there's an inverse transform to go along with it as well. Now, what is it specifically? Well, here it is specifically. Okay. Now, okay, I'm changing to f. Okay, so f of t is the original function. F of t is the original function. Here is its Laplace transform. Okay, so it's an integral. Okay, so this is called an integral transform. What kind of an integral is it? It's an integral of the function f with respect to t. We're integrating from 0 to infinity, so there's no longer, this object doesn't depend on t. The t variable is integrated out. We're summing up all the values of this integrand at all the various values of t between 0 and infinity and packaging them all up into this integral object. Now, it isn't just the integral of f. There's this other factor here, and here's where the new variable comes in. This other factor is e to the minus st. Okay. So we're integrating e to the minus st times f of t dt. Now, this is sometimes a little bit mysterious about, why is it structured like this? I make reference to a very good video lecture there. There's the link down here to it. It's from MIT, from a professor at MIT. He gives a very good extended explanation of, how it is this kind of construction came about. He describes there what it is it's kind of a continuous analog of a power series. Well, remember what a power series looks like. A power series looks like it's a way of defining a function. Let's just say a power series is a function of x, and it's this infinite polynomial in x, and there's various coefficients. That's a power series. And an infinite sum, an infinite polynomial in x, you got various coefficients. So if you throw a value of x into it and it converges, you get out a value. That value is the value of this function, capital A of x. This is a way of taking a sequence of numbers, A0, A1, A2, A3, and so on. So it's taking a sequence and manufacturing a function out of the sequence. The Laplace transform is a continuous analog of that. So it takes what's the continuous version of a sequence? A sequence is a value for every integer. Position 0, position 1, position 2, position 3, and so on. You've got a value at every integer argument. A function is like a continuous sequence. You have a value f of t at every value of the continuous argument t. for every t in the interval 0, infinity. You can't write out the values in a sequence way because t is a continuous variable. You can take any real value between 0 and infinity. And he explains it in the video step by step, and this construction turns out to be quite a natural thing. So this e to the s, or e to the minus s here, is the continuous analog, or the continuous version of this x to the power n. The e to the minus s times t. So t is the kind of indexing variable here. That goes in the power position. N was the indexing variable here. I'm going from 0 to infinity. That went in the indexing in the power position of the new variable. Well, this power position is t here, and the new variable, okay, this is an s down here, s to the power t. This is exponential e to the minus s. Okay, that's complicated detail. So we can think of it like this. It's some natural enough way of associating a new kind of function, and this becomes a function of the variable s. If you throw in different values of the variable s into here, the integral gives you different values. So you have a function of the new variable s associated to the original function f of t, because we've used all of the values of the original function f of t, defined in the positive range. We generally focus only on the positive range of t here. We've used all of those values to define the function f. Now there's various different types of notation. I'm going to show them all here. We're not going to rigidly stick to any one type of notation, because different books use different notations, and the different notations have different advantages over each other. But this thing, so this thing is called the Laplace transform of f. It's variously notated like this. Okay, here on the board I've used the capital F of s. So we quite often use the capital version of the letter for the original function as the lowercase version. So capital F is the transform of little f. Or sometimes we just put a bar over the original function letter. Or sometimes this more fancy version, we use a script L, a handwriting L. You're writing by hand, just do a scripty, flowy L. And that's good because that reminds you L, so you know it's the Laplace transform. And this emphasizes the fact that it's an operation that you do to the function. Yeah? L is an operator that you apply to the original function f to give you your new object. The operation you apply is you integrate the exponential multiplied by f. Okay? So this is a new object for us. It's a bit mysterious. We need to think about it carefully. Firstly, we got to make some remarks about convergence. This is what the transform of f of t is. But it's an integral over an infinite range. And those kind of things sometimes give you, if you're integrating over an infinite range, a function, sometimes that might give you a finite number, but sometimes the integral might not be convergent, so it mightn't give you a value at all. Now, actually, in general, the variable s can be a constant. It can be a complex number. So s is going to be an a plus ib, okay, where a and b are real. Now, of course, when you're integrating stuff and worrying about whether it converges or not, the problem about convergence is to do with how big the thing you're integrating is. And whether the contributions in the integral are small enough so that when you integrate over an infinite range, you actually just accumulate a finite result. Okay. So to investigate this a little bit, we won't deal with the convergence issues in great technical detail, but I just want to give you a flavor of it. Of course, if S is equal to A plus IB, then e to the minus st, that's going to be e to the minus A plus IB times t. And using properties of the exponential, this is e to the minus AT times e to the minus IBT. Now, how big can this thing be? We look at the absolute value of this and ask ourselves how big it might be. Well, so the absolute value of e to the minus st is going to be the absolute value of e to the minus AT multiplied by the absolute value of e to the minus IBT. Now, one of those we know kind of, so it's the product of those two absolute values. One of those we understand straight away. Remember, I don't know what A and B are. E to the minus AT, I don't really know a lot about. But e to the I times something, well, that's from that expression from Euler's equation. Remember, if you have e to the I anything, it's cosine theta plus I sine theta. So in other words, it's an element of the unit circle in the complex plane. An exponential raised to an imaginary power has absolute value 1, has magnitude 1. So the absolute value of e to the minus st is just equal to the absolute value of e to the minus AT. So the size, so the size of e to the minus st is controlled by the size of e to the minus AT, where A is the real part of S. Now, as long as A is a positive number, e to the minus AT will converge to 0 as t goes to infinity. If A is positive, then as you let t go to infinity, t is running through positive values. So you'll have e to the minus a large positive number. So that's 1 over e to a large positive number. That's going to be getting very small. Because e to the large positive number will get very big, but it's in the denominator position, so it'll make the whole thing get very small. And this convergence is quite fast. So we can expect e to the minus st times a function f of t to converge to 0 as t goes to infinity. This is speaking somewhat vaguely. We can expect this to happen for some a, which is the real part of S, for most functions, most nice functions t, nice functions f. Of all the kind of standard functions we deal with, the exponential function increases very fast. So when you put e to a minus a positive argument, it's going to decrease very fast, converge to 0 very fast. So when we form this product of e to the minus st f of t, in vague terms, non-specific terms, we can have a good expectation that that is going to converge to 0 as t tends to infinity, and it'll do so quite fast for some values of s, some values of the real component of s, for most kind of nice functions. So the conclusion being, the Laplace transform will be well defined for a lot of s, a lot of values of this new argument. And because the convergence of it is somehow controlled by this quantity e to the minus at, if it converges for any value of a at all, it'll also converge for any value of a larger than. So we tend to see convergence for these Laplace transforms in half planes in the complex numbers. So you have the plane of complex numbers, your real axis and imaginary axis. If the thing does converge for some value of a, which is equal to the real part of s, then it'll also converge for everything to the right of that line. Okay? Because every complex number to the right of this line has a real part which is greater than a. And so this thing, e to the minus at, will converge to 0 even faster for those larger values of a. Okay? So if we do get convergence for any values of s, we get convergence on the whole right-hand plane from that value of a onwards. Okay? So the Laplace transform, it mightn't be a well-defined function for all values of the complex variable s, but it will be for a lot of them in a half plane, for most nice functions, most of the nice kind of functions that we're going to consider. Okay? So this chapter will be about building up some of the theory of the Laplace transform properties that this thing has, and learning about how it is that it enables us to solve the differential equations. But a thing that we can do now in the few minutes we have remaining is to look at some example functions. So the first example will be to look at the constant function. So for all t, f of t equals 1. Pretty simple function to begin with. The 0 function would be the simplest one, but then you're just integrating zeros to get zeros. So it's not particularly interesting. So what does the Laplace transform of this function look like? Well, according to the rule, it's the integral from 0 to infinity, e to the minus st, multiplied by f of t. But f of t is just the constant 1 here. So that's simply the integral of the exponential. The integral of the exponential is e to the minus st over minus s. And we got to evaluate that at 0, and as t goes to infinity. Now, provided the real part of s is positive, when you take the limit of t, remember these are limits for t, so we integrated with respect to t. You take the limit as t goes to infinity, provided the real part of s is bigger than 0, this quantity here, this numerator, is going to converge to 0. It's going to be 0 over minus s minus the evaluation of t equals 0. And when t is 0, you've got e to the 0, which is 1. So it's minus 1 over minus s. So it's 1 over s, but only for the real part of s bigger than 0. The real part of s is not bigger than 0. The Laplace transform isn't defined. Okay, so it gives us a new function, 1 over s, which is defined on the right-hand side, the right-hand half plane, every complex number bigger than 0. Okay. Look at a second example. So if we dealt with let's Okay, you might ask about, well, what if it's not the constant 1? What if it's some other constant? Well, if it's some other constant, that constant will just be sitting here. But you're doing integration. Integration is linear, so whatever constant is sitting there can simply pop outside here. So it'll just be that constant over S. Yeah? So the Laplace transform of any constant function is just that constant over S. So the next more complicated type of function to look at would say be the function f of t equals t. Now consider for every t in the domain f of t equals t. So this is the identity function. Order 1 polynomial term, f of t equals t. Does this have a Laplace transform? And if so, what does it look like? Well, we can take the Laplace transform. Using the definitions, the integral from 0 to infinity, e to the minus st multiplied by f of t. The f of t is t. Yeah, so it's this integral. Okay, this is a harder integral. It's the integral of an exponential times t. So you got two different functions of t. Remember, you're not integrating s. S is just sitting here as this new variable that's popped into the picture. We're integrating with respect to t. Well, we can do that integral because we can use integration by parts. Okay? Because the exponential factor doesn't change that much when you differentiate it, whereas the t factor will change and will simplify greatly when you integrate it. It makes it go just go to 1. So we can do this by integration by parts. So typically we prepare the other factor as a derivative. That's the derivative of e to the minus st over minus s. So when it's written like that, when you're integrating some function times the derivative of another function, you use integration by parts. You get the product of these two, so it's t times e to the minus st over minus s. Evaluated at the limits, 0 and infinity for t. And then we subtract the integral. Now the integral of this part multiplied by the derivative of that part. But that part disappears when we differentiate it. So we got e to the minus st over minus s t. Now what kind of things do we get out of this? Well, when you look at this first term, when you take the limit as t goes to infinity, you've got e to the minus st. So as long as the real part of s is positive, this is going to decrease very fast. And even though the t is getting large, t is going to infinity, but the exponential is decreasing to 0 very fast. So this whole thing will converge to 0 as t goes to infinity. When you evaluated at t equals 0, well, you got a factor of t here, so it's just 0. So you don't get anything at all from this. You just get 0 minus 0 for this evaluation here, provided the real part of s is positive. So that's this bit here, but what about the integral? Well, the integral here, now you're integrating with respect to t, so this s can come outside on the bottom. So it's 1 over s times the integral of 0 to infinity e to the minus st dt. And that integral is just the one we did a minute ago. The integral from 0 to infinity e to the minus st, we just did that a while ago. And that was 1 over s when the real part of s was. So in total, you get 1 over s squared. Okay. So this function, pretty standard, f of t equals t, the order 1 polynomial term. It does have a Laplace transform, and its Laplace transform is 1 over s squared. What if we had a constant multiple of t? Do you need anything different for that? Well, if there's a constant multiple of t, that means there'd be a constant sitting here. You're doing integration, so that constant could just pop out here. So we would just end up in the numerator over here. Okay? So the Laplace transform of any constant multiple of t is just whatever that constant is over s squared. So this is our new function of s, 1 over s squared, that we associate to this function of t. Okay? This is the Laplace transform. Now, why this makes it easier to solve differential equations is not apparent yet. We haven't discussed that. Okay, we're just kind of meeting the transform for the first time and having a look at some things. Look at the next example there. Switch over to the notes. This third example looks at another class of function, f of t equals e to the minus at, so an exponential function. So this is quite general. You know, if a could be any value, so this could be any exponential of a constant times t. You can take its Laplace transform. We've got to integrate the product of these two exponentials. These two exponentials combine together to give a single one, e to the minus s plus a times t. Just the same way we treated e to the minus st, we can treat this, and we get 1 over s plus a. But the convergence condition is slightly different here. Here we would need the real part of s to be strictly bigger than the real part, strictly bigger than minus a. Remember, we have to have this part have a real part bigger than 0, so the real part of s would have to be bigger than the real part of bigger than minus a. As long as the real part of s is bigger than minus a, then the real part of this thing multiplying the t will be positive, so the integral will converge and you'll get 1 over s plus a. Now, you can keep doing these calculations. There's nothing to stop you trying to work out what the Laplace transform of t squared or t cubed or t to the power 4 is. Or indeed working out what the Laplace transform of sine is or cosine, etc. But we save ourselves a bit of work. We won't constantly be performing these integrals for loads of different functions. Okay? We will make use of tables. Not logarithm tables now, but tables of the Laplace transform. So the next page in the notes, what we have reproduced here is, so these are actually reproduced pages from the formula handbook. You might have seen these before when you were doing first year exams. So these will be available to you in the summer examination. And what it is it's listing a load of Laplace transforms of some standard functions. We've already seen the Laplace transform of the constant 1 is 1 over s. Laplace transform of t is 1 over s squared. We've seen the Laplace transform of e to the minus at is 1 over s plus a. And the rest of the entries here is just a whole family of standard functions. Other powers of t, products of powers of t in an exponential, sines and cosines, hyperbolic sines and cosines, and all of their neatly calculated and prepared Laplace transforms. So this will be our table for carrying out the Laplace transform in one direction and carrying out the inverse Laplace transform in the other direction. The inverse Laplace transform of any of these functions of s on the right is the corresponding function on the left. You also see a couple of new functions, Heaviside step function, the Dirac delta function. We're going to be reading those. Okay, and the second page starts to list some properties. So these are not individual functions. These are general patterns for functions. And we see a corresponding pattern for the Laplace transform. So these are some properties. The key thing to look at is how it behaves on the Laplace transform of a derivative. You'll see that it takes a derivative and it gives you a polynomial in S. That's the key simplifying movement. Okay, so we'll continue. This is just our introduction to it, just the first baby steps of it. We'll continue with this next time, and we'll get to start solving some differential equations as well.